For the Chapter 3 review sheet, we first need to find the intervals on which the function f of x is decreasing. So we know that f of x is decreasing when f prime of x is less than 0. So if we find the derivative and then find the critical values, then we can test and see where the derivative is less than 0. So first I'm going to take the derivative by the quotient rule. So we'll do the derivative of the top times the bottom. So that will just be x squared plus x minus 2 minus the top times the derivative of the bottom all over the bottom squared. And so if I simplify the top, I'm going to have a 2x squared minus x right here. So that would give me a negative x squared. And the x's would cancel. And then I would just have a minus 2. And then on the bottom, I have a x squared plus x minus 2 squared. So our critical values can be found where either the derivative equals 0 or where it's undefined. So since the top is a negative x squared minus 2, the top will never equal 0 because we'll always have a negative number. But the bottom, if we factor it, we are undefined in two spots. We're undefined at x equals negative 2 and at x equals 1. And if we check, those are actually not critical values because they are not in the domain of our original function. However, our derivative can switch from positive to negative in between those values. So our function can switch from increasing to decreasing since they are asymptotes. So we still want to check using the first derivative test for increasing and decreasing. So I'm just going to test some values. So first I'll test negative 3, and then I'll test 0, and then I'll test positive 2. And we'll plug them into our derivative. So if I plug a negative 3 into my derivative, the top will always be negative no matter what. And the bottom will be negative as well. So that will be positive. So my function will be increasing. If I plug in 0, I'll have a negative on the top. And I will have a negative on the bottom as well. So that will also be increasing. And if I plug in 2, I will have a negative on the top and a positive on the bottom. So I'll have negative. So I'll be decreasing. So the only spot where this function is decreasing will be in between 1 and infinity. So it should be none of these. Oops, I made a mistake earlier with negative 3. Because if you plug a negative 3 into the top, you get a negative on the top, and you actually get a positive on the bottom because it's a negative times a negative. So that will be a negative. So then we will also be decreasing. So we need to change our answer to C. So we will scribble out the answer for E. There we go. So C should be the correct answer. For number 2, we want to find the critical numbers of our function. So critical numbers occur where our derivative equals 0 or where it's undefined. So we're going to take the derivative of our function. So f prime of x, when we take the derivative, we'll need to chain rule. So the 3/5 will come out, and we'll have 9 minus x squared to the negative 2/5. And then we need to multiply by the derivative of our inside function, so by a negative 2x. So our function is negative 6x over 5 times 9 minus x squared raised to the 2/5. So the derivative would equal 0 at x equals 0. So that's definitely a critical value. And our function would also be undefined at 3 and at negative 3. And we need to double check and make sure that 3 and negative 3 are actually in the domain of our original function, and 0 as well. And they all are, because we're just taking the 5th root of something and then cubing it, so we can take the 5th root of zeros and negatives. So our answer would be D. For number 3, we want to find all of our x values that give us relative extrema for our function. And it looks like we need to determine whether or not those relative extrema are maxes or mins. So we'll need to do a first derivative test after we find the critical values. So in order to take the derivative of this function, it looks like it would probably just be easiest to do the product rule. So first we'll have to take the derivative of the first, which will be 2 times x plus 1, just raised to the first. And technically you need to chain rule it, but if we chain rule, we just get 1. So that's the derivative of the first times the second, plus the derivative of the second, which is just 1 times the first. So if we factor that to make it a little bit easier to see where this guy goes to 0, we can pull out an x plus 1, and we'll be left with 2 times x minus 2 plus x plus 1 to the first. And simplifying the inside, we'll get a 2x minus 4. So that would be a 3x minus 3. And then you can always pull the 3 out. Alright, so this is f prime of x. And looks like that will equal 0 at x equals negative 1. And at x equals 1. So it definitely looks like our answer would be A, but just to double check to make sure we know how to find whether or not the critical values are maxes or mins, let's do the first derivative test. So we'll test in between negative infinity and negative 1, and 1, and infinity. And I'm just going to plug in numbers in between. So we'll plug in a negative 2, a 0, and a positive 2. And we'll plug it into f prime of x. And if I plug in a negative 2, hopefully I'll do it right this time, I'll get a negative times a negative, which is a positive. So my function will be increasing. If I plug in 0, I'll get a positive times a negative, so I'll get a negative value. So my function is decreasing. And then if I plug in 2, I'll get a positive times a positive, which is a positive, so we're increasing again. Which means that negative 1 should be a maximum, and positive 1 should be a minimum, which goes with choice A. For problem 4, we want to find the intervals where our function is concave up. And we know that a function is concave up when the second derivative is greater than 0. So we'll want to take the second derivative and then do the second derivative test to look for concavity. So to do the first derivative, we need to use the quotient rule. So we'll do the derivative of the top, which is just 1, times the bottom, minus the derivative of the bottom, which is just 1 times the top, all over the bottom squared. So then the top, it looks like we'll just get 4 over x plus 3 squared. And now we'll need to do the second derivative. And in order to do the second derivative, I'm just going to rewrite this as 4 times x plus 3 to the negative 2. And then I can just chain rule it. So the second derivative is going to be a negative 8 times x plus 3 to the negative 3. And then the derivative up the inside is just 1. So my function is negative 8 over x plus 3 cubed. So it looks like my second derivative won't equal 0 anywhere, but it will be undefined at negative 3. So that's a spot where we can change concavity. And negative 3 won't be a POY because it's not in the original domain of the function. So we have an asymptote there. But we can definitely change concavity at an asymptote. So we'll just plug in some numbers to test. And if I plug in a negative 4, it looks like I will get a negative number on the top and a negative number on the bottom. So positive number, which means I'm concave up. And then if I plug in 0, I'll get a negative number, so I'll be concave down. So I will be concave up for B, negative infinity to negative 3. In number 5, we're given the second derivative of our function, and we're also given the critical numbers. And we want to use the second derivative test to determine whether the critical numbers are relative maximums. So we know we'll get a relative maximum if we take a critical number and we plug it into our second derivative and we get a negative number. And the reason that that will be a relative maximum is because we will be concave down at our critical point, which means that it has to be a maximum. So if I plug in negative 2 to 3x squared minus 4, I will definitely get a positive number. So negative 2 is out. If I plug in 0, I'll get a negative number. So I'll get negative 4. So I know that he would have to be a maximum. And if I plug in 2, I'll get a positive number. So 2 would actually be a minimum. So it looks like I have one relative maximum at 0. Number 6, we want to find the limit as x approaches infinity of the square root of 4x squared minus 1 over x squared. And finding limits as x approaches infinity is the same as finding a horizontal asymptotes. So if we take a look at our function, it's a little bit tricky, but the degree on top is actually smaller than the degree on the bottom, since we are taking the square root of x squared. We really have a situation where we have, the square root of 4, which is 2x over x squared. And since the degree on the bottom is bigger than the degree on the top, we would have a horizontal asymptote at y equals 0. Number 7 is a similar question. We want to know where we have a horizontal asymptote at y equals negative 1/2. And so we'll have a horizontal asymptote at a number when the degrees are the same on the top and the bottom. If the degrees are different, then you'll either have a horizontal asymptote at 0 if the degree on the bottom is bigger, or you won't have any horizontal asymptote if the degree on the top is bigger. So we want to look for a function where the degrees are the same, and it looks like we're either at choice C or choice A, and looks like we are at choice A since we have a 1 over a negative 2 for the leading coefficients. For number 8, we want to match the function with its graph. So first we want to take a look at our horizontal and vertical asymptotes. And the vertical asymptote would be x equals negative 2, since that would make the denominator go to 0. And since the degrees are the same with the top and the bottom, our horizontal asymptote would be y equals 1. So that looks like all of the graphs but D, so we can eliminate D. Another thing that we can check are x and y intercepts. So to find our x-intercept, it's wherever, whatever number makes the numerator go to 0. So our x-intercept would be 1. And to find the y-intercept, we plug in 0 for x. So our y-intercept would be negative 1/2. So looks like A matches up with our x and our y-intercepts. In number 9, we want to find points of inflection. So that will occur when the second derivative equals 0. So the first derivative of our function is 3x squared minus 12. And the second derivative is 6x. So it looks like we will only have a point of inflection at x equals 0. And that would be choice B. We can definitely double check that with the second derivative test to make sure that it is actually a point of inflection and not a saddle. So just a quick test, if you plug in a negative number, you'll get a negative, which means that our graph is concave down, and if you plug in a positive number, you'll get a positive to the second derivative. So it's definitely a point of inflection where we change concavity. For number 10, we want to take a look at the graph and determine whether or not our function possesses extrema on the interval from A to B. So first, if we take a look at choice A is claiming that we'll have a maximum value at x equals C and a minimum value at x equals B. And since those are two open dots, then they can't be extrema because the points have to exist. So that would not be true. For part B, it's claiming that we have a maximum at x equals C and we have no minimum value. This looks tempting as a possible answer. However, in order to have extrema, our graph has to be continuous at that point, and it's not. So that would eliminate choice B. At choice C, we have no maximum, but we have a minimum at x equals B. And again, that is an open dot, so we can't have a minimum point there. Choice D says that we don't have any extrema, and that would be correct since we are not continuous and we have open dots at the endpoints. For number 11, we're asked to graph f of x equals x to the 2/3 on a graphing calculator, and then state why Rolle's theorem does not apply. If we take a look at this graph, it looks like a cusp at x equals 0. So at first we would think that Rolle's theorem could apply because we can draw a horizontal line through our graph, which means that we should be able to draw a horizontal tangent line. However, f is not differentiable at x equals 0 since we have a cusp there. And in order for Rolle's theorem to apply, our graph must be continuous and differentiable. So the reason that Rolle's theorem apply would be C. The graph is not differentiable at x equals 0. In number 12, we are just to look at the graph of f and determine the intervals where it is increasing and decreasing. So nothing tricky here. We just want to make sure we're using the x values. So our graph looks like it's increasing from negative infinity to 0, and then decreasing from 0 to 2, and then increasing again from 2 to infinity. So that would be D. For 13, we're given that we have a relative maximum at x equals 6, and we want to choose the correct statement. So if we have a maximum at x equals 6, it means that our function must be increasing until we get to 6, and then decreasing after 6. And we have a function that increases whenever f prime of x is greater than 0, and it decreases whenever f prime of x is less than 0. So saying that f prime is negative between negative infinity and 6 would not be accurate. F prime cannot be positive from negative infinity to infinity, or else we would have no maxes or mins. F prime would have to be negative on the interval 6 to infinity. That looks correct. So choice C. In problem 14, we're given a graph of the second derivative, and we have to choose which function would represent the graph of f. So if we take a look at the second derivative is a graph of the slopes of the first derivative. So it's telling us that the slope of the first derivative is constant, and it is a slope of 1. So if we draw the first derivative, we would just want to draw a graph that has a slope of 1. So this would be f prime. And so now f prime is a graph of the slopes of f. So f prime is telling us that the slopes are negative, and then at 0 they go to 0, and then they're positive after that. So we want to take a look at a graph that starts out negative, and then the slopes hit 0, and then the graph is positive again. So that would look like choice A. And since we have some negative slopes, and then we have a minimum value right here, so the slope is 0, and then positive again. For 15, we want to make sure that f of x is a polynomial function such that f of negative 2 equals 5, and f prime of negative 2 equals 0, which means that negative 2 would have to be a critical value, and f double prime of negative 2 equals 3, which means we have a critical value, and it is concave up, since when we plugged it in we got a positive value. So if we have a critical value, he can either be a max or a min, and since he is concave up, he would definitely need to be a minimum. For the next problem, to find the x-intercepts for that function, whenever the top equals 0, you're going to have an x-intercept. So if you just set the top equal to 0 and find the x-intercepts for that function, ends up to be 3 of them. So I got negative 0.760, negative 1.376, and x equals 0.743. For problem 17, to find the slant asymptote of this function, we want to use polynomial long division. So we are going to have x to the 4th plus 1, and divide that into negative 2x to the 5th minus x to the 4th plus x cubed minus 3x squared plus 0x plus 2. And first thing we want to do is ask ourselves, what do I have to multiply x to the 4th by to get negative 2x to the 5th? And that would be a negative 2x. And then multiply that through. So that would be a negative 2x to the 5th minus 2x. And then change the signs and add them together. That would give us a negative x to the 4th plus x cubed minus 3x squared plus 2x plus 2. And then we keep going. So I would have to multiply x to the fourth by a negative 1. And we're done. As soon as you get a linear function, that is your slant asymptote. You don't have to worry about any type of remainder. So our slant asymptote would be y equals negative 2x minus 1 for this function. For number 18, we want to find the absolute minimum and the absolute maximum of the function in the interval 0 to 2 pi of y equals sine x plus cosine x. So an absolute maximum or minimum can occur at either the endpoints or at any relative maxes or mins. So first we want to find if we have any critical points. So we're going to take the derivative. And the derivative of sine x is cosine x. And then the derivative of cosine x is negative sine x. And so then we want to set that equal to 0. And so cosine x will equal sine x. And if you divide by cosine x, we have 1 equals sine x over cosine x, which is the same as the tangent of x. And the tangent of x will equal 1 in 2 quadrants. So we have to remember about all students take calculus. And tangent will equal 1 at the 45-degree angles. So that would be at pi over 4 in the first quadrant and at 5 pi over 4 in the third quadrant, where tangent is also positive. So now we're going to make a little chart and test the endpoints, so 0 and 2 pi, and our 2 critical points that we found, pi over 4 and 5 pi over 4. And we want to plug these back into our original function so we can see what the maximum and the minimum y value is. So if I plug 0 in, I'm going to get the sine of 0 plus the cosine of 0. And that will equal 1. And then I'm going to plug in pi over 4. So the sine of pi over 4 plus the cosine of pi over 4. So that will equal 2 root 2 plus 2 root 2. So that will be 2 root 2 over 2, which is just root 2. And then the sine of 5 pi over 4 plus the cosine of 5 pi over 4. So this one's a little bit tricky. They're both negative, so we have negative root 2 over 2 plus a negative root 2 over 2, which will be a negative root 2. And then 2 pi, the sine of 2 pi plus the cosine of 2 pi will also equal 1. So it looks like our absolute max will occur at pi over 4. Since the square root of 2 is a little bit bigger than 1. And our absolute min will occur at 5 pi over 4, since negative root 2 is smaller than 1. In number 19, we want to find an x value in the interval between 2 and 8, such that the derivative of that x value will equal the slope between 2 and 8. So first, let's find the slope. Let's find f of 8 minus f of 2 all over 8 minus 2. So if I plug in an 8, that will give me 10 minus 2, so that will give me 8. And if I plug in a 2, that will give me 10 minus 8, which is 2. So the slope between those 2 points is 1. So now I want to find an x value in between 2 and 8 that also has a derivative of 1. So first I'm going to find the derivative of my function. And I'm going to first rewrite this as 16x to the negative 1. So I have f prime of x equals 10 plus 16x to the negative 2, or 10 plus 16 over x squared. And I want to find where that equals 1, so I'm going to set it equal to 1. And subtract 10. So 16 over x squared will equal a negative 9. Oops, definitely made a mistake earlier when I took the derivative. There should not be a 10 there. I'm going to cross them out. Okay, so 16 over x squared would equal 1. So 16 would equal x squared. So x would be plus or minus 4. However, we only want the x value that's in the interval between 2 and 8. So we would just want the x equals 4. In number 20, we want to sketch the graph with the following characteristics. So first we know that we have a point of, at 0, 0, since f of 0 equals 0. So I'm just going to put a point there. And then they tell us that f prime of x is greater than 0. And it looks like that's for the whole graph, which means that the whole graph should be decreasing. We're also told that f double prime of x is less than 0 when x is less than 2. So that means that our graph better be concave down when x is less than 2. And then when x is greater than 2, f prime of x is greater than 2, so our graph should be concave up, which means that x equals 2 should be a POI. And it is, since the second derivative equals 0 there. So I need to make sure that my graph is decreasing and concave down to begin with. So decreasing concave down until we get to x equals 2. And then I need to switch to have my graph being concave up but still decreasing. So I'll kind of make a little saddle here and have it start to become concave up. Let's kind of try to redraw that. So it's going to be concave down. And then switch to concave up. So concave down to concave up. There we go. It's probably a little bit nicer. For 21, we want to find the horizontal asymptote for our function. And since the degrees are the same, it will be at y equals 2. And for number 22, since the degree on the bottom is bigger than the degree on the top, it would be at y equals 0. For number 23, we want to find all the horizontal asymptotes for our function. And since we're taking the square root of a square in the denominator, the degrees are the same. So our horizontal asymptote will be at 4. However, we'll have 2 horizontal asymptotes for this one, since the bottom will always be a positive number and the top will can alternate between negative and positive. The limit as x approaches infinity of our function will be positive 4. But when we approach negative infinity and we have negative x values, we will be approaching negative 4. So we have 2 horizontal asymptotes at 4 and negative 4. For this next page, I'm going to do a separate video for questions 1 through 5, but I will put question 6 on this video. So this question gives us a graph of the derivative and wants us to find the following about f. So we know that f is increasing when f prime of x is positive. So if we look at our graph, we can see that f prime of x is positive in between -2 and 0. And then it is also positive from 3 to 0. So our graph should only be increasing at those values. Our graph will be decreasing wherever the derivative is negative. So the derivative is negative in between -infinity and -4. Since it goes to 0 there, we'll break it up at -4. And then again from -4 to -2. And from 0 to 2. And from 2 to 3. Our graph will be concave up whenever our derivative is increasing. So our graph is increasing in between -infinity and -4. He is also increasing between -2 and 3. Or I'm sorry, -2 and infinity. 2 and infinity. There we go. +2 and infinity. He's increasing. Our graph will be concave down wherever f prime is decreasing. So f prime is decreasing in between -4 and -2. And he is decreasing from -2 to +2. Relative extrema. So we can have relative extrema whenever the derivative equals 0 or is undefined. So it looks like we have lots of x values where that happens. Be at either x equals -4, -2, 0, and 2, and 3. So now to determine whether those are maxes and mins would be how the derivative changes sign. So at -4, our derivative goes from negative y values to more negative y values. So we would not have either a max or a min there. At x equals -2, our derivative goes from negative to positive. So we will have a minimum there. At 0, our derivative switches from positive values to negative values. So we will have a max at x equals 0. And at 2, our derivative goes from negative values to negative values. So we won't have a max or a min there. But at 3, our derivative goes from negative values to positive values. So we will have another minimum at 3. Points of inflection occur when the first derivative changes from increasing to decreasing or vice versa. So at -4, our graph switches from increasing to decreasing. So we will have a POI there. At -2, our graph switches from decreasing. Actually, it's just decreasing to more decreasing. So we won't have a POI at -2. At 2, our graph does switch from decreasing to increasing. So we'll have one more POI at x equals 2. So now with our given x-intercepts, we're given that we have an x-intercept at -3, since f of -3 equals 0. and we have one at -1, and at +1, and at 6. Now we want to try to graph f with all of our information that we found from above. So first I'm going to put on my maxes and my mins. So I have a max at x equals 0. So it doesn't matter where I put them. Put them right here. And I have some minimums at -2 and at 3. It's a couple minimum values. And let's see. We'll start from -infinity. So we know that our graph is decreasing from -infinity to -4, but he also needs to be concave down. So we're kind of decreasing, and we are concave down. And then at -4, we are concave up. Oops, let me erase that. So we are decreasing, but we are concave up. Okay. And at -4, we switch to being concave down, but we are still decreasing. So we're decreasing from -4, go through our x-intercept till we get to -2. And at -2, we are still concave down, which means that we need to make a little cusp, which kind of makes sense that the derivative would then be undefined at that point. There we go. And we are concave down in between -2 and +2. So we'll stay concave down through this maximum. We'll stay concave down. All right, until we get to about 2. And then when we get to 2, we need to switch to being concave up. So switch about there. And then we'll go through that minimum point. And then in between 2 and infinity, we remain concave up, and we are increasing from 3 to infinity. I think I made the wrong little symbol up there. Let me fix it really quick. There we go. And we'll just go through our x-intercept at that point. There's our lovely graph. One thing I want to change is because our derivative is undefined at 2, just want to make more of a saddle type of situation through 2 so we can get a vertical tangent line going on. Alright, there we go. For number 7, we first want to find f prime of x. So I'm going to take the derivative and get 20/3 x to the 1/3 minus 20/3 x to the -2/3. And then I'm going to take the second derivative and get 20/9 x to the -2/3 plus 40/9 x to the -5/3. So to find my critical values, I first want to find where the first derivative equals 0 or is undefined. So set that equal to, well, first I'm going to factor out a 20/3 x to the -2/3, which would give me 1/3 minus a -2/3 would be 3/3, so that will just be x minus 1. So my two critical values would be at 0. So that would make it undefined, and at x equals 1. And then to find my relative extrema, I'm going to do the first derivative test. So I'm going to test between negative infinity and 0 and 1 and infinity. And I'm going to just plug in a -1 and a 1. Let's go with a 1/8. Easy to cube root. And a 8. So if I plug in a -1, I will get a positive times a negative, so I'll get a negative number. I'll be decreasing. And if I plug in 1/8, I will get a positive and a negative, so I will also be decreasing. And if I plug in an 8, I will get a positive and a positive, so I will be increasing. So it looks like I have one minimum at x equals 1. And then to find my POIs, I'm going to set that equal to 0. So I'm going to factor out a 29th, x to the -5/2, or 5/3, which will give me a -2 minus a -5 as an x, and that will be +2. So it looks like my possible points of inflection are at 0 and at -2. Then I will do the second derivative test to check the concavity. So negative infinity to 0. To -2. That should go first. To 0 to infinity. And I will plug in, I have to cube root again, so plug in a -8 and a -1 and a +8. So if I plug in a -8, I'm going to get a negative times a negative, which will be a positive, so I will be concave up. And if I plug in a -1, I'm going to get a negative times a positive, so I'll get a negative. I'll be concave down. And if I plug in 8, I will get a positive and a positive, so I'll be concave up. So I think I've answered all the questions, and now it's time to graph f and f prime on the same coordinate axis. So before I graph, I'm just going to find the x-intercepts really quick. So for my original function, I'm going to factor out a 5 and an x to the 1/3. So I'll be left with a x minus 4. So I'll have two x-intercepts at 0 and at 4. And then I know that I have a minimum at 1, so I want to plug 1 in. And I have a minimum at 1, comma, -15. So way down here, I'll have a minimum. And no maxes. And I'll have a POI at -2, so I'm going to plug a -2 in, see what I get. So 5 times -2 to the 4/3 minus 20 times negative 2 to the 1/3. And that is not very nice functions. So let's see. Maybe easier to plug it into factored form. So 5 times negative 2 to the 1/3 times a negative 6. So that would be definitely a positive number. So 30 times the cube root of 2. Let's just put our point kind of up high here. And then I'll have another POI at 0. So thankfully that was already graphed. So before we get to negative 2, we are concave up, but we're still decreasing. And then we get to negative 2, and we switch to being concave down. And then at, we're just concave up in between 0 and infinity. So that is our beautiful function. You know, I'm going to put my point a little bit lower so we can see our POI. So we'll just pretend it's more like right here. So we're concave up and then concave down. Oh, it's kind of hard to graph on this thing. Okay. There we go. Okay, so now we want to graph our first derivative on the same axis. So first of all, in our first derivative, we know that we have zeros at 0 and at 1. And we also know that we have a max or min of our derivative at our points of inflection. So we should have a let's see. Definitely we'll have a 0 at 1 because we have a min there. So our slopes will go to 0. But our slopes start off very negative and then they remain negative until we get to 1. And then they become positive. So we have slopes that are negative. And they remain negative till we get to 1, and then our slopes are positive after that. So that would be a graph of our derivative. For number 8, we first want to find the domain and the range. So our domain would be from negative infinity to negative 2. I'm sorry, to 2. And then from 2 to infinity. So that should be a positive 2. Since 2 is the only spot that will make the denominator go to 0. And our range, let's see. It looks like no matter what, we will always get a positive number. And our horizontal asymptote, since the degrees are the same, will be at y equals 1. So our range should be from 1 to infinity. Where is our function increasing and decreasing? We will have to do the derivative test for that. So first let's do the quotient rule to get our derivative. So we'll do the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So it looks like we can factor out a 2x and an x minus 2. And we'll be left with a x minus 2 and a minus x, it looks like. So that's over x minus 2 to the 4th. So it looks like our derivative will be negative 4x times x minus 2. All over x minus 2 to the 4th. So then that x minus 2 can cancel out, and we'll have negative 4x over x minus 2 cubed. So now our function will have two critical values at x equals 0 and x equals 2. And we can do our first derivative test to figure out where our function is going to be increasing and decreasing. So I'm going to plug in a negative 1, a positive 1, and a 3. So if I plug in a negative 1, I'm going to have a positive number on the top and a negative number on the bottom. So it will be negative. My function will be decreasing. If I plug in a 1, I'm going to get a negative number on the top and also a negative number on the bottom. So positive increasing. If I plug in a 3, I'm going to get a negative number on the top, but a positive number on the bottom, so then I'll have decreasing. So it looks like I'll have a min at x equals 0, and I'll have a max at x equals 2. To figure out the points of inflection and the concavity, we'll need to do the second derivative and then the second derivative test. So the second derivative is the derivative of the top times the bottom minus the top, so plus a 4x, times the derivative of the bottom, all over the bottom squared. So simplifying that, looks like we can factor out a negative 4 and an x minus 2 squared. And we'll be left with a x minus 2 and a negative 3x. And so then we can cancel the x minus 2 squared with the x minus 2 to the 6. So we'll have a negative 4 and a negative 2x minus 2. So I'll just factor out that negative 2x. So we'll say this is a positive 8. And this is just a x plus what? Double check that, make sure I did that right. Yep. And that's all over an x minus 2 to the 4th. So it looks like we could have two possible POIs, and that would be at x equals -1 and at x equals 2. So we will do the second derivative test. So that will be from -infinity to -1 to 2 to infinity. So I'll pick -2, 0, and 3. Plug it into the second derivative. So if I plug in a -2, I'm going to have a negative on the top and a positive on the bottom, so it will be negative and concave down. If I plug in a 0, I'm going to be positive and positive, so it will be concave up. And if I plug in a 3, I will also be positive and positive, so it will also be concave up. What I didn't notice before was that 2 cannot be in our domain. So we cannot have a max at 2. Let me cross that guy out. Also, we wouldn't be able to have a POI. But it's still good that we used them in our first and second derivative test because we do have an asymptote at x equals 2. And we still want to know what our function is doing on either side of our asymptote. So I'm going to put my asymptote on at x equals 2 and at y equals 1. And we do know that we have a minimum at x equals 0. And if we plug in 0, we will get 0. So we have a point at 0, 0. Alright, so a minimum value there. And then, let's see. If we take a look at our first and our second derivative test, we know that our function is decreasing and concave down until we hit -1. So we need to be decreasing and concave down. And then we hit -1 and we have to switch to being concave up. And then when we hit 0, we begin to increase. So now we need to be increasing and concave up until we get to 2. Looks like we will kind of cross our horizontal asymptote at this point and go up from there. All right, and it's probably going to make it a little bit more concave up looking. Okay, there we go. And then at 2, we are just concave up the entire time, but decreasing. So it will be right here. And we have no more maxes or mins at that point. So I need to change my range a little bit because we can get some numbers that are smaller than 1. So my range will be from 1 to infinity and also from bracket 0 to 1. So now we still need to graph the first derivative. So from 2 to infinity, I know that my derivative will have very negative slopes, and then the slopes will get closer and closer to 0, but never get there. So that would be that half of the first derivative. And so then for from -infinity to 2, my first derivative has slightly negative slopes, and they get closer and closer to 0. So we'll have some slightly negative slopes that hit 0 at 0. And then the slopes become pretty positive pretty quick. So we'll just have it kind of match and get really positive really quick. For number 9, we want to graph f of x equals 3x to the 4th plus 4x cubed. So first we're going to find the x-intercepts for this particular graph. So we're going to factor out an x cubed, and we'll be left with 3x plus 4. So we'll have x-intercepts at 0 and at negative 4/3. To find our extrema, we're going to take the derivative. So we'll get 12x cubed plus 12x squared. And to find the critical points, we'll factor out a 12x squared. So we'll have critical values at x equals 0 and at negative 1. Then we can do a first derivative test to see where our function is increasing and decreasing, and where we have some maxes and mins. So I'm going to test -2, -1/2, and 1. So if I plug in a -2, I'm going to have a positive and a negative, so that'll be negative decreasing. If I plug in a -1/2, I'm going to have a positive and a positive. So I will be increasing. And if I plug in a 1, I will have a positive and a positive. So I will continue to increase, which means that I have one minimum at -1. And if I plug -1 into my original function, I will have 3 minus 4, so my minimum will be at -1, -1. For my second derivative, I get 36x squared plus 24x, and we can factor a 12x out of that, and we'll be left with 3x plus 2. So I will get possible POI at x equals 0 and at -2/3. So then we'll do the second derivative test to test for concavity. And, whoops. Okay, so I will plug in a -2 and a -1/3 and a 1. So if I plug in a -2, I'm going to get a negative times a negative, which is a positive. So I should start by being concave up. And if I plug in a -1/3, I'm going to get a negative and a positive, so I'll be negative and concave down. And if I plug in 1, I'm going to get a positive and a positive, so then I'll be concave up. So now it looks like I'm ready to graph my function. So I have x-intercepts at 0 and -4/3. And I have a minimum at -1, -1. And I have POIs at 0 and at -2/3. So when I graph it, I'm going to be first concave up until I hit -2/3. Then I have to be concave down and continue to increase, but after 0 be concave up. So that is my graph of F.